I'm Anna Quach, and my research is in random forest. I'm currently a PhD student at Utah State University, and this is located in Logan, Utah, and I'm working under Adele Cutler. So today I'll be talking about random forest. I won't be talking too much about my research, really. But my research is in random forest, and I'm making advancements in random forest specifically for genome-wide association study and the visualization part of random forest. So making random forest more interpretable. Okay. So I'm gonna share my screen right now so that you can see my slides. All right, so I'll be talking about tips and tricks for building a random forest classifier. So this won't be too much of an introduction to random forest. I'll give a brief overview of what random forest is, but I'm gonna assume that you know the basics, so you should know what a decision tree is. And I'm gonna focus on classification. So just with the response variable that's categorical. Okay, so we won't be talking about regression in this case. Here's basically an overview about what I'm going to be talking about. So this is actually the second time I've talked with AI with the best. The first time I gave a talk, the title was Random Forest, the Vanilla of Machine Learning. So in that talk, I basically gave a really good, I guess, overview about random forests and all the resources available and just kind of the background of how random forests came about. Okay, and so you can, if you Google like the title, or you can Google Anna Quach, AI with the best, then you should find my slides at SlideShare. So why use random forests? So I'm guessing that most of you are just interested maybe in learning random forests or using random forests, or you've already used random forests, but you want to improve the method on your particular data set. Okay, so I think one of the reasons why random forest is popular is because among statisticians and non-statisticians, is because it can perform well if you just basically just simply apply a random forest model and you don't have to do any tuning. You just use all the default settings for the parameters and it does well. And that's really nice. And another thing is that it can basically do, classification, regression. It can take any type of data set, and it has quite a few capabilities. Okay, and then one of the things that's nice that random forest is popular for is that it can handle more variables than observations. So data sets such as the one that I'm working on right now is from the genome-wide association study, and it has millions of variables, millions of genetic variables, and observations in the thousands. And something like linear regression would not be able to handle that, but random forest, it does fine with that. So random forest is actually pretty popular in genetics type of data. So we'll talk a little bit about the random forest algorithm, some common misunderstandings, not only in just how to build a random forest model, but random forest itself, like who invented it and so forth. And then common mistakes when building a random forest model. And then one example here would be just not growing enough trees. And then we'll talk about that towards the end of the talk on how to determine how many trees to grow. Okay, so funny thing is that not everybody knows who invented random forests. And it was Leo Breiman who came up with the algorithm back in the early 2000s or maybe late 1990s. So the paper on random forests actually came out in 2001, and he's the only author on that random forest paper. And And this is Adele Keller, who is my advisor, and she worked with Leo Breiman. So when she was doing her dissertation with Leo Breiman at Berkeley, she actually didn't work at random forest at that time. Like, Leo Breiman didn't invent random forest at that time. She worked on a couple different other projects in optimization and archetypal analysis. But after she graduated with her PhD under Leo Breiman, she came to Utah State University, and she was working on mixed models or mixture models, and she was actually unhappy with that research area just because she couldn't find any applications. So she actually emailed Leo Breiman and said, "Hey, do you know what I could do? I don't, she was interested in doing something different." And so Leo Breiman replied in the email and said, "Hey, we should go to the NIPS conference." Okay, so she went to the NIPS conference, and she was just so inspired and excited about what they were doing. And so that's how she got involved in random forest. So they sent emails back and forth, and Adele Cutler is the one that helped Leo Breiman develop the random forest code. So if anybody asks, these two are the developers of the original random forest code, but Leo Breiman is the main inventor. Okay, so like I said before, there's quite a few capabilities of random forest that I think other machine learning algorithms aren't capable of, such as one being that it provides a rank of variable importance. It has ability to impute missing values. It's robust to outliers. It can handle big data sets, so more predictors than observations, or a lot of observations and few predictors. It can handle correlated variables and more. And like I said, it's able to do regression and classification. Okay, and the nice thing is that it's easy to get good performance out of random forest, just without any tuning. Just apply random forest and you can get pretty good accuracy. Okay, so what is random forest? I usually like to say that it's basically an ensemble of decision trees. So well, what's the difference between a random forest and a decision tree? So random forest is a collection of decision trees. So in a decision tree, you're making binary splits. And at each node for each tree, it's looking at all possible variables. Whereas in random forest, it's only going to look at a subset of variables that were randomly chosen and then determine which set or which variable out of that set of variables best separates the classes. Okay, and the second difference is that when you build a tree in random forest, you're building each tree on a bootstrap sample. So you're gonna take a sample with repeats, and that's gonna be your bootstrap sample. You're gonna grow each tree on a different bootstrap sample. So when you take a bootstrap sample, basically you end up having about 2/3 of the observation in the bootstrap sample. And then a third of the observations are left out, and we call that the out-of-bag sample. Okay, so those observations that are not in the bootstrap sample are in the out-of-bag sample. Okay, and then a classification tree, you're basically building the tree on the whole sample, okay, not on the bootstrap sample. All right, so like I said, random forest was originally implemented in Fortran. Some people think it was first implemented in R, but it was first implemented in Fortran, and it's actually available for free at this website here. And if you just search random forest, this is one of the web sites that comes up. And then if you just click on like software, then you should see that you can download the code. And then after random forest was implemented in Fortran and that was made open source, then a guy from industry actually took the original Fortran code and interfaced that into R. And he mixed in a little bit of C code in there. but the package is called random forest. And then after that, you know, other softwares or other packages were made. So these are two of the packages that I know that is just basically random forest, but they made it a lot faster. So they used C++ or they parallelized random forest. So you should get basically the same results as in this random forest package or in the from the Fortran code. And I think actually like there's a paper on this one where they show that they get the same results as in this package here in the Fortran package. Okay, so last time when I talked at AI with the best, I worked with a data set that you can get from this link here. And he's a professor at from the CS department here at Utah State University. So if you're interested, you can download the data set from this website. And I think you might have to email him to get it. But it was on detecting fake likes, so determining whether a Facebook like is fake or real. So there's basically just 18 features, and then just a binary response variable. All right, so to build a random forest model in R is pretty simple. So you're going to just use the random forest function. So you'd have to load the package, obviously. And then you use the random forest function, and then you just specify your response variable until dot. So I'm going to use all the predictor variables available, and then list my data set, and then importance equals true. So this is, you don't necessarily need to have this. This is basically calculating the permutation importance. So here it specifies you're doing classification, okay? And then you're building 500 trees, and that's the default number of trees grown, and then the number of variables tried at each split. So I talked about how random forest at each node is going to randomly sample a subset of variables, and then of those subset of variables randomly selected, it's going to determine which variable best separates the classes. So here we're randomly sampling 4, okay, and that's just the square root of the number of predictors, and that's the default. And then you have the out-of-bag error rate, so OOB. So that gives you the estimate of the test error. So I talked about how each tree in a random forest is gonna be built on a bootstrap sample, and the observations that aren't in the bootstrap sample are the out-of-bag sample. So to get the out-of-bag error, you're gonna use the out-of-bag sample, okay? So to basically get that, so the observations that aren't in the bootstrap sample, you're gonna throw that down each tree, and then you're gonna see where each observation falls, which terminal node it falls in, and that gives you the predicted value. And then you also have, you know, the ground truth. And so basically the proportion of times the sample that are out of bag gets misclassified, and that's going to be calculated in each tree, and then you average that misclassification error from each tree over all trees, and that gives you your out of bag error rate. So here it's only 11.5%, which is pretty good. And then you have your class error rate. So this is the error rate for the first class here, which is, okay, that's a fake like. And so that's basically just calculated by taking the 93 and dividing that by 607 plus 93, and that gives you your class error. And similarly, you can do it with this, but you're going to take 68 and then divide that by the sum of these two values, and that gives you your second class error for the real class. All right, so when you're building a random forest model, there's a couple of things that you should take in consideration of. So definitely you want to check out the out-of-bag error rate. So typically you want an error rate that's small, okay? And then you want to make sure you grow enough trees. And I'll show you a bit later how you determine that. And then there's parameters that you will want to optimize. So typically in classification, there really is just usually most people just optimize mtry, but you can also optimize depth, which is specified as node size in the package. So usually mtry does well with just the default value, but if you want to optimize random forest, you want to change these two and determine which mtry and which node size gives you the optimal accuracy or the minimum error rate. So node size here, the depth of the trees, are basically determine how deep a tree grows, basically by what you specify here, what the user specifies here. So one's the default. So you're going to grow this tree very deep until the node size is the terminal node is basically left with one observation left. Or you're going to grow the tree until you reached a node where it's all pure. So it's all in one class, either all, real likes or all fake likes. Or you're going to stop growing any further because you can't split that variable any further. So in this case, I mean that for that particular variable, all the values are the same. All right, so variable importance in random forest. So I actually get asked this question quite often. Oh, so there's a question here. So somebody said, what is square root of p? So p is the number of predictors. So for example, in this data set here, I have 18 predictors. So the square root of 18 is roughly about 4, and that's what mtry is set to. So usually I get a lot of questions about variable importance in random forest. So I'll be programming in R, obviously, since I was talking about R packages. So by default, if you set importance equals true in one of your arguments in the random forest function, then by default, it's going to show you 2 variable importance plots. One is a variable importance plot using the permutation importance, and then another plot using Gini variable importance. So first, let's talk about the 2 different measures of importance. So Gini importance you can think of as the rough and ready measures, and this is basically calculated using the Gini index. So you can simply say that the Gini importance is basically the mean decrease in node impurity. So when you make a split on a variable, you can calculate the Gini index, and then you can calculate the weighted Gini index on the daughter nodes. Okay. So the difference in the Gini index that you calculated from the parent node versus the daughter nodes, okay, that decrease, that difference there, is going to be average over all the trees for that particular variable, and that's how you get the variable importance measure for just one of the variables. Okay, that's why I'm saying it's the mean. So you're averaging over all the trees, the decrease in the node impurity. And then permutation importance is an interesting measure of variable importance, because basically what it is that for each tree, so we talked about the out of bag sample, and you can throw that out of bag sample down the tree and get your predicted value, and then the difference between the predicted and ground truth basically can give you misclassification error. Okay, so we have that, and then let's say we take that out of bag sample and then we scramble just one variable. We scramble one variable, we throw those observations down the tree, and then we can also calculate the predicted value, and then the misclassification error for the scrambled observations that are out of bag. So the difference between those two error rates is going to give you a measure of permutation importance, and you're going to average this over, for that particular variable, over all the trees, and that gives you the global permutation importance. Was talking about which variable importance measure to use. I basically would suggest using the Gini importance for these three different conditions. So it's suggested that you should use Gini importance when the data set is huge, just because to calculate Gini importance, it's not as computationally expensive. And if you want to use Gini importance, you can use it just to reduce the number of variables. So an example would be where I was talking about the genome-wide association study, where they have millions of genetic variables and then observations in the thousands. So it would be typical just to use, the Gini importance from random forest to get rid of all these variables. And then from there, you can do something with that subset of variables. And then another thing is there was in this other paper that talked about how Gini importance is basically biased if you have mixed data set. So you have some categorical and some continuous. So it said that in the paper that the Gini importance tends to choose the continuous variables at each node more often than categorical variables. So I would suggest if you have a data set where all of your features, all your predictor variables are all the same data type, so all categorical or all continuous, then it would be appropriate to use Gini importance there. So other than that, permutation importance is generally a better measure of variable importance. The only downside is that it is computationally expensive. And so one thing I'll do note here is when I talked about using Gini importance for this data set, it's not only because there's a lot of variables, but when I was running some simulations, I also found that for some reason, which was very interesting, that Gini importance actually did a better job at detecting the causative genes in comparison to permutation importance. And so there are actually a couple of papers out there that have said that Gini importance is better, and later I will publish that as well, that it is in fact better in this case. As to why, we're not sure yet. Okay. All right, so one of the mistakes I've seen people do, and actually when I was starting out using just learning random forest and using random forest, I made this mistake as well, is that when I was running a random forest model and I looked at my variable importance plot, by default, and this isn't something that Leo Bryman and Adele did in their Fortran code. This is something that Andy Leah, who interfaced the random forest code into R, came up with. He, by default, included variable importance plots that have been basically standardized or scaled. So basically what it's doing is when each tree is grown, you can get a variable importance measure for each tree, and that variable importance measure is going to differ between all of the trees. So if you calculate the standard deviation of those variable importance measures from all these trees, then you can get a standard error, and that's something that you can obtain from your random forest object in R. And so basically he took the importance value and divided by the standard deviation. And then that's what you're getting here is these scaled importance measure. And you actually don't want to use the scaled importance variable measure, okay? And then, so specifically when you plot this plot here, your important variables, then you want to specify scale equals false. And then I do get a lot of questions from my friends or other people that have asked me, okay, which plot do I use? Okay, so there's this left plot here that says, in this x-axis, and this says mean decrease in accuracy, which is determined from the permutation importance, and then the mean decrease in Gini is the Gini importance. Okay, so like I said before, permutation importance is generally a better measure of important variables. So you typically want to use this left plot here and unscaled. So we have a question here. So it says, what's the reason not to use the scaled? So, so back when Leo Breiman and Adele were implementing this, the reason why they came up with why there's this scaled value here is basically they wanted to test whether they grew enough trees so that these variable important values measures here have stabilized. So that's the reason why they have that in there. But you don't really want to use the scaled. It's fine just to use the unscaled. The scaled variable importance doesn't really do anything. Well, if you don't grow enough trees, you're going to see a difference there. Okay, so, and I'll show you that. Let's just talk a little bit about like growing enough trees and stuff. So I'll get back to that in a bit. So let's talk about how many trees we should grow. Okay, so first thing, you want to grow enough trees so that your class errors have stabilized. So in this example here, I basically have two classes. I have the fake likes and then the real likes. And then I have, let's see, there's another question. What are some of the problems with random forest classifiers? Okay, so I'll just get back to that. So I'm gonna, if that's okay, I'll answer your question after I talk about how many trees to grow. So first thing, you want to grow enough trees so that the class errors have stabilized. And then second, after you've grown enough trees, so this is true, then you want to make sure that the variable important measures have stabilized. Okay. And then third, so this is basically, the second one is basically dealing with what I was talking about in here, where you have those standard deviations. So the variable important measure is going to vary from tree to tree, and the standard deviation is calculated on those values. And then third, after you've grown enough trees so that this is true, then you want to make sure you grow enough trees so that the proximity measures have stabilized. Okay. And proximities are, I feel like, are not used as much as the variable important measures. And this is something I've been working on for my dissertation. And so I'll talk a little bit more about what proximities are in just a bit. Okay, so first thing is class errors. So we have the two classes. We have the fake likes and real likes, okay? And as you can see here, so we have our error rate on the y-axis, and then how many trees are grown. So in here, I'm just growing 500 trees. And as you can see, the error rates basically have stabilized pretty much after, I'd say, 100 trees. And so we could have just grown 100 trees, and that would have made random forest a little bit faster. But basically, I think it seems like 100 is pretty good, but you might want to go out a little further just in case. Okay, so that looks good. It looks like we've grown enough trees so that classifiers are stabilized. And then secondly is we want to make sure that the variable importance measures have stabilized. So what does that mean? So here I'm not using the scaled values for my variable importance. And so this is only going to be affected by the permutation importance, by the way. So here, this is just for illustration purposes. I'm only using 5 trees, but that's crazy. Nobody would just grow 5 trees in random forest. So if we look here, if 5 trees are grown, this is what we get from random forest. And then if we grow 1,000 trees, you can see here that there's differences in the rank of the variable important measures for the permutation importance. And so I'll just go back and forth, and you can see here that there's some movement in the ranking. So I personally think it's obviously going to be okay if, like, you know, these two variables switches, just because their variable importance measure is quite similar, and I would say it's just by chance that they switch. But you know, if one of these variables down here switches with like year active, then obviously you haven't grown enough trees. So you want to grow enough trees so that there's not much movements in this ranking, basically. And then the proximities. So the proximities are basically calculated by looking at the out-of-bag sample. So the observations that are out of bag, we're going to keep track of the two observations, and we're going to do this for each pair of observations. So let's say we have 2 observations. We put them down the tree, and then they're both out of bag. We're going to see where each of these observations fall. And so the proximity is calculated by taking the proportion of times the 2 observations fall on the same terminal node, and you're going to average this over all the trees. Okay. And so what's nice about proximities is that it helps us identify outliers, and it helps us identify any structure or any clustering in our data, so we can look for basically a cluster of observations that are similar, and those set of observation might be important in certain ways compared to other groups of observations that are clustered together. So basically, you'd have to use interactive plots to really interpret the proximities. And so that's something I did for my master's thesis. So here we have 2 proximity plots. So this one, I only use 5 trees. And this one, there's only 1,000 trees. So I would say in this right plot, this is what random forest proximities basically looks like. And so if you see something like this, you should be worried. So this you don't have to worry. So it usually looks like something like this. So if I had 3 classes, then I'd have like 3 spikes, and that is normal to me. So I colored these by different classes. So here, you're not growing enough trees. There's actually dramatic differences between these 2 plots. Okay, so you want to make sure so you have enough trees so that your class errors are stabilized, and so that your variable importance measures are stabilized. And so to make sure that your proximities have stabilized, you have to grow even more trees than the stabilizing the variable important measures. So I listed them in this order for a reason. So this can stabilize quite quickly. this takes longer to stabilize. It's going to need more trees than this here. And then the proximities measures to get those to stabilize is going to need more trees than stabilizing this, than the second one here. All right, so, and then one of the other things, which is kind of interesting, and this is something I had a discussion with my advisor, is that she's seen a lot of people make this mistake, is that when they're predicting on new data, they don't put in new data here. So what they end up doing is just using the training set to make their predictions, and that's obviously wrong. You want to set aside your test set, and then this is what you want to put in there. So the untouched test set that you set aside is what you want to input here. Okay. All right, so another interesting thing that I heard is just another way of measuring variable importance. So we saw previously that this variable here is the most important variable, okay? And you can make a cutoff, by the way. So you see this big jump here in variable importance. I would make a cutoff here and say there's really only one variable that is important in predicting whether a Facebook like is real or not. So let's say if we want to make sure if this is actually important, then we can drop that variable out and then observe what happens to the out-of-bag error rate. So before we drop that variable, this is what we got. Okay, and I'm just using the default settings here. So the out-of-bag error rate is 11.5%. So let's see what happens after you drop that variable. Once you drop that variable, the error rate does increase. And it increases by about 4%. So I'd say it seems like 4% is pretty big in my opinion. And so I think entropy is actually an important variable there. Okay. All right, so I have gotten questions about random forest, how they built a random forest model and they didn't understand why random forest did poorly. And so I'd have to kind of understand what that person did. So it might not be that random forest really performed poorly, but you need to compare it to different models to get an idea if it really did perform poorly or not. So usually what I do when I'm analyzing data is I don't just apply random forest, but I make sure that it is also performing well. So you really want to pick the best model for your data. And so for classification, what I usually compare random forest against is support vector machines, linear discriminant analysis, and just like a single classification tree. So support vector machines is not as interpretable as random forest, but it is known to do well in classification. And then linear discriminant analysis and classification tree are more interpretable. So basically I have a spectrum. So I have these machine learning algorithms that are known to do well in prediction, and then I have some that are more interpretable. Okay. And then for regression, I compare it usually against gradient boosting machines, linear regression, and a regression tree. Okay. And so once you compare your random forest model, you know, if you do like cross-validation or something like that, and you compare the error rates, then you can get a sense if random forest actually did poorly or not. Okay. So it might not be that it didn't do so bad. It might be that the features that you have are, maybe most of them are not that important, you know, so maybe you need to collect data and find more features that you think are associated to your response. All right, and then the last tip I have is just, you know, you really just need to understand your data. When it comes down to it, if you want the best random forest model, you do have to make sure what you're getting makes sense. And it's really just thinking about, you know, what features you should include in so forth to help improve your random forest model. All right, so if you think of, let's say, a question on random forest after this talk that you just, remember later today, you can email me at my Gmail account, and I'm happy to answer questions or give you advice on how to improve your random forest model for your particular data set. All right, so let me see. There's a couple of questions that I need to go back and answer. So let's see. So what are some problems with the random forest classifiers? I'd say, I guess, like, they're one of the problems I know. Well, it's maybe that's more for regression. So I'll mention regression a little bit because this comes up kind of quite a bit when people are like comparing random forest and other regression models, is that if you have a data set where there's only linear association and the best separator of your data is basically a line, then something like a linear model would do better than random forest. Random forest classifiers. I'm trying to think what problems there would be with classifiers. I don't really know that many issues with the random forest classifier. But I know that if you compare like random forest on like maybe image detection, so right now like neural networks or deep learning is quite popular in classification. If you compare random forest with, let's say, neural networks or deep learning, random forest doesn't do as well. So I know that that's one of the problems where random forest doesn't do well. Okay, and then somebody asked, let's say, could you talk a bit also on scaling? Is this scaling on the permutation and importance measures? So that's a question for Gilbert. So Gilbert, if you want to reply to that. And then somebody else asked, is random forest actually better than gradient boosting? Great question. So, so there's a paper, and there's actually, well, two papers, because there's a paper that compared a bunch of machine learning methods on using the UCI or the machine learning repository, which is public available data set. So they took those data sets there, and that's, I think, probably around 200 data sets that they used, and they compared all the machine learning methods, and they found that random forest was one of the top methods. And so I think generally, from what I've experienced and what I've heard, gradient boosting does do better than random forest. But gradient boosting, the downfall of using gradient boosting would be to take the time to really tune it so that it does better. But I think gradient boosting is generally better. So let's see, Gilbert, you said you meant scaling this time in terms of memory. Oh, okay. So random forest, it's embarrassing parallel. So you can, like I mentioned, so I'll bring up slides and show you the packages that I've listed. So I listed two packages, and I think these are fast implementation of random forest. So if you have big data, then you want to use one of these packages that parallelizes random forest. So random forest can be easily parallelized. So I'll mention a little bit about my research. So I was working with the genome-wide association study data sets, And there I'm looking at quite a few predictors and not as many observations. So I say, like, in general, for machine learning methods, if you have a lot of predictors, then your chances of detecting, like, let's say, the true causative variable decreases if you have more and more variables. So that's something is an issue for random forest, but also I think other machine learning methods have an issue with as well. Yes, so yeah, the curse of dimensionality is basically the problem there. So Gilbert, you said voting procedure. So are you wondering how the voting procedure works in classification? So I wish I had a tree drawn in here, but basically when you have your tree and you throw your observations down that tree, it's going to be classified as either, a real like or a fake like by doing a majority vote. So what that means is basically in that terminal node, if the majority of observations there, let's say, are fake, then you'd classify the new observation that falls down that tree as fake. All right, well, Gilbert and everybody else who asked questions or came to listen to my talk, like I said, if you have questions, I'm happy to answer them later. If something comes up in the future, if you want to email me about random forest, then I would be completely happy to help you with that.